Hello, so in today's lesson, our learning target is I can represent real-world constraints with linear inequalities in two variables. So if you recall in our last two lessons, we explained and went over examples of how to represent real-world situations and problems using linear equations. So today we're kind of going to do the same thing, but with different types of problems that are better represented using inequalities rather than equations. So a lot of what we're going to talk about today is very similar to the last two lessons, but there are a couple little tweaks that I want to emphasize. So first off, we see the word constraints. So a constraint refers to some sort, this isn't a very precise definition, but some sort of restriction. So some examples of constraints would be, if you only have, say, $80, you're not going to be able to buy anything that costs more than $80. So $80 is kind of a limit to how much money you can spend. Similarly, on our campus here at Wasatch Academy, you're constrained in the distance you can walk from campus. So for example, we have Wasatch Academy here, we have, say, Wheelers here, we have Main Street here, Main Street, and we have Terrell's here, but you can't, and we can put Maverick here, but you're kind of constrained. You're not allowed to walk, say, 6 miles up the road to Fairview. So your distance is constrained. You have constraints on the amount of distance you can travel from campus. So it's easy to talk about these constraints, but it's a little bit harder to put them into numbers mathematically. So, well, like I usually like to do, let's start with an example problem. So suppose you go shopping at the mall. T-shirts cost $10 and video games cost $25. You have $300 to spend. Represent and graph the constraints using linear inequality. Okay, so first things first, let's analyze the problem a little bit. So we're shopping at the mall. T-shirts cost $10, video games cost $25. We have $300 to spend. So represent and graph the constraints using a linear inequality. So first off, we know that we're going to set up an inequality. And on one side, we're going to have the amount of money we have to spend. And then on the other side, we're going to have the amount of money we actually spend. So how much money do we have to spend? We're given it right here in the problem. We have $300 to spend. So we have 300. And then on the other side, we're going to have the amount of money that we actually spend. So is the amount of money that we actually spend going to be greater than or less than the amount of money we have to spend? So think about our example. if we want, we can just buy, say, like 2 t-shirts. We can only spend $20 if we want. But we can't buy 100 t-shirts and 50 video games. That would be way more. So we need to make sure we have the right inequality sign. We're going to have 300 is greater than or equal to, because the amount of money that we actually spend has to be less than 300. So now we have to figure out how to represent the amount of money that we actually spend. So let's look at this problem again. So we have 2 other key pieces of information. We have that t-shirts cost $10 and video games cost $25. So the way that we're going to want to represent this is by writing t-shirts, which we can represent using a T, cost $10. So we're going to have 10T, because each t-shirt costs $10. So we can say T represents number of t-shirts. We can have plus 25V, where V represents number of video games. And this is our inequality, because we're going to be paying $10 for each t-shirt and $25 for each video game. So here's where it differs a little bit from an equation. So there's nothing inherently dependent or independent about either of these variables. So we're going to have to just kind of pick one to be on the y-axis and pick another one to be on the x-axis. So why don't we just arbitrarily pick that t will be on the y-axis and v will be on the x-axis. So we have 2 real choices in how we want to graph this. So in these equations like this, we're only concerned about positive money and positive amount. We can't buy negative t-shirts or video games. So I'm only going to graph this one quadrant here. So you said we're going to have t, which would be the number of t-shirts on the y-axis. We'll have v, which is the number of video games on the x-axis. So there are 2 main methods we can use to graph this. One that we can use is we can find the x and the y intercepts. So to find the x and the y intercepts, first we would change this to an equality, and to find the y-intercept, we would set x equal to 0, which in this case, we would set v equal to 0. So we get 10t plus 25 times 0. So that's just nothing. We divide each side by 10, and we'd get 30 is equal to t. So that's 10, 20, 30, and I can plot that intercept over here. So now if I want to find the x-intercept, once again, I would set y equal to 0, or t equals 0, which 300 equal to 10 times 0 plus 25v. So go away, divide each side by 25. 300 divided by 25 is equal to 12. So we get 12 is equal to v. We can get 4, 8, 12. And then we have 2 points. We have it's greater than or equal to, so I could just connect them with a solid line. And now we want to think about our problem a little bit. We're not going to be able to buy more than 30 t-shirts, right? Because if we bought 30 t-shirts, 30 times 10 is equal to 300, so that's our maximum amount. Similarly, we're not going to buy more than 12 video games, because 12 times 25 is equal to 300. So what that means is that we would shade below the line, because we can buy fewer t-shirts or fewer video games, but we can't buy more. And this is the graph of our scenario. So another way that we could have graphed that if we wanted to is we could have, say, subtracted 25 from each side, so we'd get 300. So I'm going to switch this around, so I have 10t is less than or equal to negative 25b plus 300. And then I could have divided each side by 10. We could have gotten t is less than or equal to negative 2.5v plus 30. And if you notice, our graph is the same as this one. It's just in the slope-intercept form now. Our y-intercept is 30, our slope is negative 2.5, and t is less than or equal to that, so that's why I shaded in below the line. And the really cool thing about graphing these is we can really easily see whether or not we could get a certain combination. Like, if we look here, we can just look at this graph and see that we could afford to buy 2 video games and 20 t-shirts, right? And we could plug the numbers into the equation to see if it works. We could have 300, 10 times 20, so that would be 200 plus 50, and you see that makes sense, right? So we could buy that many. However, we would see that we probably couldn't buy 8 video games and 20 t-shirts. So this point wouldn't work. And like, if we wanted to, we could buy all video games. We could buy 12 video games, but we wouldn't have any money to spend left over for t-shirts. Or we could buy 30 t-shirts and have no money for video games. So if you want to have kind of a good balance between t-shirts and video games, you could pick a point here. Like, we could say buy 5 video games and 14 t-shirts. But again, we can really easily see what combinations we can buy. So that is an example of how to represent this set of constraints using a linear inequality in 2 variables. So going forwards, I'm going to do in the next lesson another example of a similar but slightly different real-world inequality problem, and just how to model that using linear inequalities. Yeah, so that's it. Stay tuned for that video. Hope this was helpful.